Happy Tuesday. I'm going to remind you again, we only meet one time next week. Next Thursday is Thanksgiving, so we don't meet. And then we only have 1 week after that, I think.
Really?
Yeah.
Is that the exam?
We're reaching, because the week after that's already the 1st of December. So we're already getting towards the end, which is apparent because we're now looking at line integrals. First, a review of conservative vector field. Right, so we did that already. It's just here again. Right, so not too worried about that. Line integral. Also called a path integral. Right, so these are really cool integrals. So whereas before you were integrating over an interval, well, that's a direction. You're going along a line on an axis. I'm talking single integrals. Either the x-axis, the y-axis, or it could be a z-axis, whatever. Well, we can actually integrate over any curve. This is what's called a path integral. So C is a curve defined by the parameterization R of t over. Sorry, did you shave it?
Yeah.
Okay. Thought so. I'm going, who the hell is this guy here? Thought shaving would get you out of the pit of doom, but it doesn't. So the path is only going from T1 to T2. There's actually two types of line integrals. There's one for scalar function, so we're letting f be a scalar function. Then the integral over C of f dr is called a line integral or a path integral. And what you're doing is you're integrating along C. So that would be read the integral along C of f with respect to r. dr now is a length differential. Right, we use r because we use r of t for the parameterization. We may also see it written as ds. S is typically used as length, or dl, right, for length, but it's a length differential. To calculate it, it's just the single integral from t1 to t2 of f evaluated at r times the magnitude of r prime dt. So what does it mean to evaluate f at the parameterization? Well, it just means you replace x with the x of t, y with the y of t, z with the z of t. Right, remember, this is going to be a multivariate function. And then you're, oh look, I actually wrote ds down there. That's a mistake. That should be dr. And then your dr becomes the magnitude of r prime dt. By the way, this now allows us to rewrite an arc length integral that you learned in Calc 2. Integral along C of dr is the length of the curve C, which is arc length. Fundamental theorem of line integrals. This is an extremely important theorem. Do not forget it. That's not what's supposed to be next. How did my slides get out of order? That is very worrisome. Why are you down there? You should be up here. Yes, you should. That's what I was going to say. Okay. And you can also do a line integral of a vector field. Right, it's now written as f dot dr. Still integrating along C. Evaluating this is very similar. It's the integral from t1 to t2. F evaluated at r. Now it's dot r prime dt. Let's work. So that is the work it would take to move a particle along C through a vector field, a force field F. Oh dear, now we're dealing with force fields. Fundamental theorem of line integrals. Suppose that F is a conservative vector field on domain D with potential V. If R is any path along a curve C from P to Q, then the integral along C of F dot dr is V of Q minus V of P. In other words, the integral is path independent. How you get from the start to the finish doesn't matter. This is only if your force field is conservative. As a corollary to this, if it's a closed path, then the integral is 0. So this symbol here just means circulation. And it just means that your path is closed. So like if you integrate over the entire circle, that would be closed. So it's just you start and end at the same point. That is a closed path. And I have been known to do this. In fact, I have done it. Where on an exam, I'd give them a vector field to integrate over. And something like that was the path, C. And I said, find the circulation along C of F. And laughed watching everyone trying to parameterize C instead of showing that F was conservative. In which case it's automatically 0. I think only 2 in that one class, 2 out of like 40, realized, oh, F is conservative, it's 0, I'm done, and moved on. Everyone else tried to actually parameterize that really nasty curve. It amused me. So in some problems, it might be nice and they actually give you the parameterization. Other problems, you're given the curve and you have to parameterize it. Going along -1 to 2. The integrand, y e to the x squared. Evaluate that integrand over the parameterization. Y gets replaced with -3t. X gets replaced with 4t. It is now times the length of the derivative of r. What's r prime?
4 minus 3.
dt. What's that magnitude? We can also factor out that -3. So we wind up with a -15. Integral -1 to 2 of t e to the 16t squared dt. That's the setup. Now it's just a matter of evaluating that. Oh, well that's just a Calc 1 integral. Tying everything back in. How would you evaluate that?
U equals t squared. Du equals 2t dt. Or u equals.
I mean, you could theoretically do that, but then you have to do another substitution.
U equals 16 t squared.
Yes. Like, 'cause you wanted to write it as e to just some variable. Right, again, you could do that, then you'd have 16u, but then you'd have to do a w. So I might as well just say u is 16t squared. What is du?
32t.
Do we have a 32t dt?
Yes.
We do.
Well, you have a -15. You have a t, which is
We have a t dt, so I just have to divide by 32. And then the antiderivative of e to the u is just e to the u. Two squared times 16.
64.
-1 squared times 16. There's your line integral. Because I don't like negatives, so that leading negative irritates me. I'm sorry, not e to the fourth. I did 64 divided by 16, not minus. This would be e to the 48.
just remind us again what exactly that tells you about the givens? Is that length of?
This is just straight up an integral.
Okay, don't worry about it, basically.
For a scalar function, I don't quite remember what the
Okay,
interpretation
all right.
is.
That's fine. Okay,
If that wasn't there,
right.
it would just be the length.
Oh, okay, all right.
Right. Vector field those work.
Okay, that one's work. All right. And if that with
And I think you can also count it as flux.
all right.
But we very rarely use a single integral to represent flux. That's double integrals.
Okay. And if that was 1 ds, that would be length. Yes. Okay, cool. Thank you.
But that would have to be a scalar.
Right.
Yes, not the vector.
Right. Okay.
In this case, they just tell you what the curve is, not the parameterization. That means, sadly, because of the way things worked out last semester, one of you are at a disadvantage. Because we didn't really get to cover parameterizations in Calc 2 because of the way the semester worked out. So you need to go ahead and brush up on that through the chapter. I think the Calc 3 book starts with that. Chapter 1 is the end of Calc 2, which is the parameterizations and stuff. The first thing we need is the parameterization for the curve. This one is fairly straightforward because it's a circle. We should know that parameterization. Parameterization of the unit circle.
Goes like this.
You can use t. I just use theta because it's angles. I prefer theta. This is also where direction matters. Curves have directions. How are you traversing it? Well, this they tell us counterclockwise. What's the domain then? And in this case, it is less than or equal to 2 pi. Because we are actually doing one complete traversal of the unit circle to return to where we started. If that was clockwise, this would not be the correct parameterization.
Be 0 to negative 2.
2 pi to 0.
Yeah, or because you wouldn't be able to write this,
Oh.
right? Because that doesn't make sense. What you could do is you could do that, negative 2 pi to 0. That would work. Yeah, that would work. Right? Because you're starting at negative 2 pi, you have to go clockwise to 0. But yeah, you could also integrate from 2 pi to 0, but you have to be careful. You have to write something like from theta 1 equals 2 pi to theta 2 equals 0. Something like that. Or you can actually change the parameterization itself in a way that allows you to keep 0 to 2 pi and still signify a clockwise direction. negative, I think you just multiply by a negative. I think that would work. But in theory, there's an infinite number of ways to parameterize any given curve. Even this one, you don't have to do that.
So,
Now, what I am going to do is I'm going to draw that like that as a circulation.
so to start, R of theta, we call that the parameterization of C.
That's the parameterization of C.
Of C. Okay, thank you.
Evaluate the integrand along R. Times the magnitude of R prime. What's R prime?
Sine theta, cosine theta.
P theta. What is that magnitude?
1.
Oh. This is sexy. Let 6 pi, how did I get so quickly?
When you plug in 0 and 2 pi for the trig terms, they're the same for 0 or 2 pi, so it's just the,
For the trig terms?
well, yeah, like cosine of 2 pi is the same as cosine 0.
True.
So when you do, like, well, you do sine theta plus cosine theta from 2 pi to 0.
Yes, that's what I was trying to
Get
get
0.
at. But that's not what I did. I didn't actually evaluate the antiderivatives. I knew they were 0 right off the bat. How did I know that? And you can't just say because I've been doing this for 2+ decades. It was a property of integration that I used.
It would be periodic.
If you integrate over any multiple of the period of a periodic function, it's automatically 0. What's the period of cosine of theta?
2 pi.
And we're integrating over a multiple of 2 pi. That's automatically 0. What's the period of sine theta? And we're integrating over a multiple of its period. That's automatically 0. You're just left with 3, which is a constant, so it's 3 times the length of the integral, or of the interval. That length is 2 pi, so it's 3 times 2 pi, which is 6 pi. A very useful property, don't forget it.
A whole number multiple, right?
That's the definition of multiple.
All right, all right, gotcha. Thank you.
Half is not a multiple.
Okay,
By definition, it has to be an integer.
okay, thank you.
And remember, -5 times something is still a multiple.
Okay,
So
yeah.
you can multiply by a negative number, it's still a multiple.
Yeah, okay.
That's not going to really matter in this case because you're looking at length of an interval. If that's a multiple, so it's really always going to be positive because length's positive.
Right.
But you can, right? So -2 pi is a multiple of 2 pi. It's -1 times 2 pi.
Yeah.
So circulation. Remember, that means we start and end at the same point. Does it matter what point we choose as our starting point? Nope. Because we're going to go back to it anyway. So why not start at the origin? And notice that there's a direction that is counterclockwise, viewed from above. I don't think the view matters just yet when we do surface integrals. It will. Because it'd be like when viewed from above or when viewed from the front, it does change the orientation. So how are we going to do this?
Figure out if f is a conservative vector.
Do you see a vector?
Conservative field.
Do you see a vector field?
Well, I don't know, but it's got f and we got the integral.
Right, that's a scalar function, isn't it?
I don't know.
Do you see vector components?
No.
Nope, so that's a scalar function. So sadly, fundamental theorem of line integrals does not apply. You can only use that on vector fields. Yeah, that's why I threw this in here to get your hopes up. Right, because you could have done this, you could have tried to do the same thing there if it was a vector field, because there's circulation, but it wasn't.
Will it require some kind of piecewise evaluation?
How many paths do you see?
4.
We have to break this into 4 different paths. And then we sum up each path integral. You think that's bad? Wait till we get to surface integrals and it's a cube. How many surfaces are there on a cube? Oh, don't worry, I have that example. It is a pain in the ass. This is why I pointed out that it doesn't matter where we start. So I'm going to choose that to be curve 1, path 2, path 3, and path 4. Again, there are an infinite number of ways to parameterize this path. I am going to choose the parameterization such that t goes from 0 to 1 for all 4 of them. So if you want t to go 0 to 1, how would you parameterize that first path?
T0.
T comma 0. What about the second?
Is that 1t?
What about the third?
One minus t1.
And what about the fourth? Now, I could also make use of another property of line integrals, which states that if the only difference between the path is a flip in the orientation, then those two line integrals only differ by a negative. So I could parameterize, for instance, C3 to be in the same direction as C1, right, which would then be t comma 1 from 0 to 1, but then subtract instead of add, because it's the opposite direction. That would also work if you wanted to do that. All right, you could do the same thing for C4, just flip the orientation, so it's the exact same thing. It would be 0 to t from 0 to 1, but then you subtract instead of add. So that's what I said. There's so many different ways you can approach these. So I'm just going to write this out. I am not going to include the function ds. Just signify what we're doing. So because I broke the path up, and again, notice how it was broken up. A union of non-overlapping paths. So if your path is a union of non-overlapping paths, then the path integral is the sum of the path integrals. So that's what we're doing. So integral from 0 to 1. It was what? ds over x squared plus y squared plus 1. So evaluate that 1 over x squared plus y squared plus 1 over the first parameterization. What is it?
1 over t squared plus 1.
Times the length of R1 prime. Well, what's R1 prime?
Oh, 1, 0.
I agree the length is 1. I'm just going to write this out for now. Until you get the hang of it, I wouldn't skip any steps. And then dt. And you write that is going to be 1, so. Plus integral from 0 to 1. Now, evaluate the exact same function, this time over R2.
T squared plus 1, 1 over t squared plus 2.
Plus what you said?
Plus 2.
Yeah.
X is 1.
What is R2 prime?
Zero, 0, 1.
Same function. Evaluated along R3. And you don't have to worry about expanding.
1 over 1 minus t squared plus 2.
What is R3 prime?
Negative 1, 0.
Same function, but now evaluated along R4. And again, you don't have to worry about expanding.
1 over 1 minus t plus 1. Squared. 1 over 1 minus t squared plus 1.
What is R4 prime? Oh. Crud. Fucker. What is R4 prime?
0, -1.
What do you notice about all of the lengths?
Just one.
Almost as if there was a method to my madness. Antiderivative of 1 over t squared plus 1.
That inverse tangent of t.
Oh, and aren't all the intervals the same? So I don't have to evaluate out each piece individually. So what I'm going to do is I'm going to write out the sum of all of our antiderivatives and then write the evaluation. What is the antiderivative? 1 over t squared plus 2.
Uh, 1 over root 2 inverse tangent t over root 2. That was just a wild guess.
It's also on your sheet. That sheet, remember I handed out the table of integrals? It's right on there. It's one of the basics. Antiderivative of 1 over the quantity 1 minus t squared plus 2.
Is that 1 over root 2 inverse tangent 1 minus t squared over root 2?
Close.
Negative that.
Is it negative what he said?
Yes.
Still not correct, but closer.
Okay. Getting there.
One minus t over root 2.
It's just 1 minus t, not squared. And what is the antiderivative of that final term?
Minus the inverse tangent of 1 minus t.
What is the inverse tangent of 1?
Pi over 4.
Of 0?
0.
0. What is the inverse tangent of 1 over root 2?
Is that one pi over 6?
Is it just 1? We just write it as inverse tangent 1 over root 2.
Okay.
It's just the inverse tangent of 1 over root 2. It does not have a nice answer in terms of pi. And of 0, oh, that's nice. Now it's 1 minus 1 is 0, okay, so that's nice. Oh, well, minus negative 1 over root 2 inverse tangent of 0, or not 0, 1 over root 2. And then you'll see it's also minus negative inverse tangent of 1. So there's the integral. Pi over 2 plus root 2 inverse tangent of 1 over root 2. Or inverse tangent of root 2 over 2 if you prefer. What did that pencil ever do to you?
Wrote pretty well. Had a good eraser.
And so you reward it by throwing it.
I tried to catch it.
Now that pencil's eraser's going to look, I'm not going to erase for you.
Honestly, it might.
If I was that pencil, I would. But I'm petty. Good? So fairly straightforward, right? Again, what is the hardest part?
Setting it all up.
The setup. The setup is like 60, 70% of the battle. So find the total work done in moving a particle in the force field ZZX along the helix cosine of t, sine of t, t, from t equals 0 to t equals pi over 2. Remember, work is just the integral along c of f dot dr. Oh, well, they gave us r. That's nice. That means the work done. The integral from 0 to pi over 2. F evaluated along R. dotted with r prime. So what's r prime?
Negative sine t cosine t 1.
What is that dot product?
Negative t sine t plus t cosine t plus cosine t.
What's the period of cosine? What are we integrating over?
Pi over 0, pi over 2.
Is that a multiple of?
No.
No. Oh, bummer. Well, at least that term still won't be too difficult.
And then at least we get to do integration by parts.
How many times?
Twice.
Those last two terms each require integration by parts. Or formulas number 37 and 38 on the integral table. Or a calculator. Well, what is the antiderivative of cosine?
Sine.
I don't remember which one's 37 and which one's 38. But the antiderivative of t times cosine. Let's make sure I have the order right in here. Cosine of t plus t sine of t. Antiderivative of t sine of t is negative t cosine of t plus sine of t. But there is that minus out in front. And that whole thing will be evaluated from 0 to pi over 2. This would be really evil of me to put something like this on the exam and then say, oh, by the way, you can't use any integration aid. Well, that's not too terrible to do, at least. Could be really evil. Make it something like e to the t sine t, e to the t cosine t, and e to the t tangent t. Now, why use sine cosine? Maybe I'll use secant, cosecant, cotangent. That'd be really evil. I like it. Sine of pi over 2 is what?
1.
What's sine of 0?
0.
Cosine of pi over 2.
0.
Cosine of 0.
1.
Oh, that's nice. Sine of pi over 2. Remember, that's also times pi over 2 now. And sine of 0 doesn't matter because 0 times anything is 0. And we know that sine of 0 exists because sine is defined everywhere. What is cosine of pi over 2? Oh, that's nice. And then cosine of 0 doesn't matter because it's 0 times it. Sine of pi over 2 is 1. And sine of 0 is 0. So when all is said and done, you get pi over 2 minus 1. They don't tell us what units we're in, but what are the SI units for work? The joule. So we have a force field given. Want to find the work done in moving a particle once around the circle in the xy plane with its center at the origin and a radius of 3. Assume positive orientation. I need to remember to correct that. So we're going around the circle once in the counterclockwise direction. First things first. Need a parameterization.
You say counterclockwise or clockwise?
Counterclockwise.
So 3 cosine theta, I believe, since the radius is 3. And then 3 sine theta.
Zero.
Oh, wait.
Zero to 2 pi.
Zero to pi. This is a circulation. Is that conservative? So take the force field and evaluate it along R.
Six cosine theta minus 3 cosine theta, or sine theta, comma 3 cosine theta plus 3 sine theta, comma 9 cosine theta minus 6 sine theta.
What is R prime?
Negative 3 sine theta. 3 cosine theta. And it's still 0.
That last term being 0 is nice. That last component being 0 is nice. That means we don't have to worry about the last component in the first vector. Sorry. You're not minus there, are you? You're plus. You have 5 seconds. What is that integral?
0.
Time's up. It's 18 pi. Both those evaluate out to 0. Because you're going to do u sub either sine or cosine. Both have a period of 2 pi. And you get from 0 to 2 pi. So both of those are gone. This is just 9. 9 times the length of 0 to 2 pi, 18 pi. Noticing these little tricks can greatly shorten how long you're working on the problem. Unfortunately, the exam is not only a test of knowledge, but also a test of how well you manage your time. So little tricks like that can be very, very helpful in an exam. Good so far?
Is it 18 pi because the sine squared, cosine squared, it's just 9?
It's 9 sine squared plus 9 cosine squared is 9. And then the other two terms evaluate out to 0 because they're both periodic.
Over the interval.
Actually, I could also use the double angle identity there and say that is sine of 2 theta. Both of those are going to be a sine of 2 theta, which is pi periodic. So sine times cosine is actually pi periodic, and we're integrating over two multiples of the period, which will be 0 anyway. And either way, it's 0. Oh, that's this one, okay. Find the work done in moving an object from 1, -2, 1 to 3, 1, 4 through the given force field. What's missing?
Parameterization. You have to parameterize this movement from that point to that point.
How would you do it?
I'm kind of guessing here, but you turn that into one vector, right?
Did it tell you it's a line?
No, it didn't. It didn't tell you it's a line.
I think you actually.
So what's missing?
Well, you need to know how the force field affects it.
That's kind of what we're going to be doing
Right.
to find work.
All right.
How are you moving from point A to point B? What's the path?
You're supposed to get that from the force field, right? No.
I would just assume it's direct. So so straight line.
That's a bad thing to do.
Why?
Assuming gets you into a lot of trouble in math and physics. So the fact that you had to assume is your answer. That's what's missing. They don't give you a path. They give you a starting point and an end point. They don't tell you how to get from A to B. That should be your first clue.
Work done means, like, it's not total work, so work is just, you can.
Oh, this is total work.
Oh, just, okay.
Whenever we're doing a work problem, it's always total.
Alright. So never mind.
Right? Because even if I say, so even if I start with a large line, I'm just using line as an example. And then I go, okay, well now I only want half. I'm still finding total work, but now just of a shortened interval. Right, so it's still total. So whenever you do a physics problem with work, it's always total work. The huge clue is this force field ought to be conservative. Because then we have path independence, which means then, yes, you can do the direct. Straight line would work if it's conservative. So if you get a problem and all they do is they tell you you're going from point A to point B and they don't tell you how, that is a huge flag that this is probably a conservative force field, which means we're going to be using fundamental theorem of line integrals. So check it. Is that force field conservative? If it's not, then the answer would just be the work depends on the path taken, and we can't figure that out. There's not enough information. Well, how do you determine if it's conservative?
If del cross F is 0.
Another way of saying that is curl free. And so you may hear me refer to it that way. That's what I mean. It's the zero vector.
If curl equals 0.
If the curl is the zero, you have to be careful because it doesn't equal 0. It equals the zero vector.
Okay, if curl equals 0.
Right. We typically say it equals 0 to mean that.
Right.
It's an implied vector, but just realize it
Yeah.
means it's the zero vector.
Should always be
That
the vector.
equals.
I got it. Thank
Because
you.
curl is always a vector.
Yeah. Okay.
Partial z. I'm sorry. Partial y. Of this.
0.
What's partial z?
0.
Oh, okay. That first term is 0. Hey, we're off to a good start. I have to do this one next. Partial z.
3z squared.
Partial x.
3z squared.
Partial y. I'm sorry. Partial x. Partial y.
2x.
This is conservative. Which means you have two ways to proceed from here. You could use any arbitrary path from point A to point B. Obviously, line is the easiest way to do it. Parameterize that line, and then proceed as we have been. Or, what did the fundamental theorem of line integrals say the integral was?
V of q minus v of p.
Where V is what?
The potential of that.
A potential.
A potential event.
Because remember, potentials are unique only up to a constant, so theoretically it's an infinite number of potentials. So that's the second path we could take. And just find a potential for the force field, and then do V of, since I was using point A to point B, V of B minus V of A. Because we haven't had practice finding potentials, that's the route that I'm going to take. We're going to go ahead and find a potential for this force field. So remember, if it's conservative, what does that mean?
You can get to it with a gradient.
Right? That means that there's a function V such that V is del F. Right? In physics, we use negative del F. Semantics, doesn't matter. It says the same bloody thing. I'm sorry. Wow, I really screwed that up. It's F equals del V. Again, physics, it's technically negative del V, but again, semantics, we don't care. It's the same thing. But what's del V? Just that, right? And I won't write this step out every single time. That means that V has to satisfy three conditions. V sub x has to equal the first component of F. I'm not going to have enough room, so I'm going to move that down the line. Vy has to equal the second component, and Vz has to equal the third component. Simultaneously. The way a lot of books do this is by observation. Do not like that method. They'll solve all three of those equations and then compare the results. I do not like that method. Do not like it at all. So the method I'm about to show you is probably different than the textbook.
And this will give us a potential for
Yes.
the F.
Specifically, I'm going to find the simple potential,
Okay,
the one in which the constant is 0.
right. Potential for that F.
Pick one of the three equations to solve. Doesn't matter which one you start with. The easiest one to start with is V sub y. What's that antiderivative?
X cubed
One
over.
over x. Yes.
X squared y.
Oh, why? Jeez.
You're not done yet.
Plus a constant.
Plus a function of x and z.
Plus some arbitrary function of both x and z. Right? When you take a partial of a function only of x and z, it's 0. So in terms of dy, that acts as a constant. I'm going to call that, let's call it, I'm going to stick with little v. Our goal now is to find that function. Or we have two other equations to look at. Pick an independent variable, x or z, to differentiate with respect to. It doesn't matter. Which one do you want to do? Z? What is the derivative of x squared y with respect to z?
Zero.
What about v1 of xz?
So derivative with respect to z.
Yeah.
is, 0, 1.
I see you did something very common. I'm not differentiating what's inside. We're differentiating the entire function.
It's that thing where you just put the function there and then put dz next to it, right? Z, okay, partial z.
It's just the partial with respect to z of the function. But what does that have to equal?
X squared.
Three x z squared.
Has to equal 3x z squared. So what does v1 have to equal?
XZ cubed.
It have to be the antiderivative of that with respect to z, right? Which is
Plus V2
of.
Y or X1.
So in this case, you actually don't need y,
Oh, because we already did it. That's why we're doing this. Okay.
right? Because v1 was a function only of x and z. So v2 would have to be only a function of x. Can't be of y. So here's where we're at right now. And again, I may wind up skipping this intermediate step here. We now have to find what that v2 is. Well, there's only one variable left. Differentiate with respect to x. What do we get?
2y. 2xy plus z to the third plus v2 sub x of x.
In this case, we don't have to do a partial. You take a partial of a function strictly of x with respect to x, it's the same as a regular derivative. You're not incorrect if you write sub x.
Okay.
Right, just technically you don't have to, it's a regular derivative. What does that have to equal?
2xy plus z to the third.
So what does v2 prime have to equal?
0 plus, yeah, just 0.
So what's v2?
C.
Some arbitrary constant c. We can let that c be any number we want. So why not say it's 0? So there's a potential for V, or for the vector field. This is where you have to pay attention to the question. If it's saying find a potential for this conservative vector field, you can let C be 0. Right, because you're only looking for one. You could let C be any number you want, right, because you're only looking for one. If it says find all potentials, then you have to keep C as an arbitrary constant. Family of them. We're not done yet. All that was just so we could use the fundamental theorem of line integrals. I really don't know why it does this. What's V evaluated at 314?
201.
What is V evaluated at 1, negative 2, 1? So total work done is 202 units.
Is the cabin recalling? Do you need to go fight against a rising pain?
No, it's saying that I have my Calculus 3 meeting 1 hour ago. Actually, now an hour and 20 minutes ago. You know, for a supposed smartphone, it's not very smart, is it? Where's my physics person? What a shame. Does this look familiar? Oops.
Well, one half that V squared is kinetic energy, and V is a potential, so VA is potential energy.
So what is this saying?
Prove the conservation of energy.
This is the conservation, well, a form of conservation of energy. Specifically, energy is conserved in a conservative vector, in a conservative force field. So your change in energy is 0. It's only one of the most important laws in all of physics. Conservation of energy law. Conservation law that you may not be familiar you do not lose information. Which was the biggest flaw in Stephen Hawking's original black hole theory. Is that in his theory, information was lost. Which is a violation of fundamental principles of physics. So we're going to prove this. And this might be all that I'm able to, this might be the last thing we do tonight. What is Newton's second law?
F equals under.
Technically total. Some forces, but we're going to leave it this way. I think I discussed this in this class. Was Newton correct?
No.
No. Newton made a fatal flaw.
That was you trying Mercury.
Did he do that?
Yeah, I'm pretty sure.
Well, Newton made several fatal flaws. He forgot to take relativistic effects into consideration, and that mass is not actually constant. Mass is a variable. But how could he have known? I mean, general relativity didn't come out for another, what, 200 years? 200, 300 years?
Sounds like a skill issue. Yeah.
That's what I say. I mean, come on. Newton, you claim to be the smartest man of your time. You didn't know about general relativity? It's no excuse. If we take the derivative of v squared, v squared is just v dot v, right? Vector v dot of vector v. Which by product rule is that, right? And dot product is commutative. So you can write that as 2v dot a. So what we can conclude is that v dot a is 1/2 the derivative of speed squared. Work. Is the integral along C of f dot dr. But f is ma, and dr v dt. Oh. But a dot v. One half ddt of speed squared. A path goes from A to B. So it's the integral from A to B of d dt v squared dt, all times m over 2, right? Those are just constants. So we get 1/2 mvv squared minus 1/2 mva squared, which I'm just noting happens to be change in kinetic energy. So work is change in kinetic energy. On the other hand, we're told F is conservative, so F is negative del V. Therefore, work also equals negative del V dot dr along the path C. Which is VA minus VB. Which is negative change in potential.
So what we did to go from F to W is flip the gradient sign.
No, that's not really what we did. But wait, on the one hand, work is delta K. On the other hand, work is negative delta V. They have to be equal. It's the same quantity. Rearranging terms. Keep it in the form that they had. We get our desired result. Starting energy and ending energy are the same. So congratulations, you've now graduated to the point of proving one of the most fundamental laws of all of physics. And again, probably the most important law of all of physics, conservation of energy. For a special case, this was through a conservative vector field. Conservation of energy only applies A, through a conservative vector field, or in a closed system, right? If you actually just look at the Earth, energy is not conserved. You lose thermal energy. Heat radiates away. If you just look at your car system, right, when you're driving, you have kinetic energy. You stop, your kinetic energy decreases, but what increases?
Thermal.
Thermal energy. Your brakes heat up. Now let's say you were parking your car. You get out of your car. Say you went home, right? So it's for the night. You come out 12 hours later. Your brake's still hot. What happened to that energy? It dissipated away. Energy was not conserved. It's because your car is not closed. It's not a closed system. But that is not a violation of conservation of energy, because it wasn't a closed system. We're not going to do this. I'm just pointing out here that this F here is the gravitational field. And it is, in fact, conservative. Gravity is a conservative field. I would recommend you try to work through that problem on your own. Because in doing so, you're going to find the potential for gravity. And I'll just discuss this one. You take the cross product of F, set it equal to the zero vector, solve for B and C. You're going to have a system of three equations and two unknowns.
The cross product, I'm sorry, the cross product of F.
The curl of
The
F.
curl of F.
Set it equal to the zero vector.
Okay.
Right, which means each component of the curl has to equal zero. That gives you your three systems.
Okay.
System of three equations and three unknowns. Well, two unknowns. Solve for B and C.
Okay.
That's how you would solve that one. Right, why? Because what's a gradient field? Conservative.
It's a conservative field, no curl. No curl.
Questions on line integrals?
None yet.
Oh, what's next? Oh. Thursday is surface integrals. Again, I wish my physics person was here, because there's two surface integrals. You have the scalar, and you also have fields. Well, the surface integral of a vector field has a special name, and anyone who studied physics cringes at it. It's called flux,
Flux. Huh.
which is a flow rate. Flux integrals are a pain.
Well,
Surface integrals in general are a pain.
I guess
So that is Thursday, surface integrals. Then we go into Tuesday, Green's theorem, Thanksgiving break, two more theorems after that, and then review and final.
Wow.
I think there's one more project coming up too,
Yes. At
right?
least
Because you're currently working on project 4,
I think it's 4, yeah.
and then project 5 is after that,
Yeah. 4 is due on
the 26th. So you have your 4th project due on the 26th,
Right.
and you also have 3 homework assignments coming up. One due tonight, one due Thursday, and then one due next Tuesday.
Project 4.
Okay.
And if I'm not mistaken, next week is the assignment of project 5.
Okay.
There's a 5th one?
Yeah.
Before the end of the year?
Has to do with
Yeah.
yeah, it has to do with line integrals, surface integrals. I think it's more specifically using Green's theorem.
Hey, we didn't.
said, this is where